Hello students, welcome to EPG Pathshala. I am Dr. Varun Vyas from Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about the module Bridges Controlled Circuits Part 2 from the paper Measurements and Instrumentation. In this module, we will study about AC bridge circuits. First, we will look into the classification of AC bridges. Under the AC bridges, we study about capacitance comparison bridge and its variant Wein Bridge. And then we will study about inductance comparison bridge and resonance bridge circuit. In previous module, we looked into DC bridges and now we will study about AC bridges. AC bridges can not only be used for measuring resistance but also for measuring inductance and capacitance. The unknown quantities can be a resistor, a capacitor, or an inductor attached in series or in parallel in one of the arms of the bridges. The working and the principal operation behind the AC bridges is similar to the Wheatstone bridge. In LCR bridge circuit, that is resonance bridge, three electrical components, resistor, capacitor or inductor, are in series. Whereas in other types of AC bridges, one may have two components in series or in parallel. AC bridges can be broadly classified into capacitance comparison bridge and inductance comparison bridge. Both Wein and resonance bridge circuits measure unknown quantities via combination of capacitor, inductor, or resistance either in parallel or in series in one of the arms of the bridge circuit. Here our objectives are same, that is to balance two arms of the bridges, and the potential drop is measured by a null detector, that is a galvanometer. AC bridges. Let us first look at the capacitance comparison bridge. In order to understand the capacitance comparison bridge, it is important to understand bridge balance equation as shown in figure 1a. Potential at point C and D should be equal in terms of amplitude and phase. Therefore, for a balanced bridge, potential drop from point A to C should be equals to A to D. These potential can be written as EAC is equals to EAD. This is equation 1. According to Ohm's law, potentials can be written as I1 dot Z1 is equals to I2 dot Z2. This is equation 2, where I is the current and Z is the impedance of the capacitor or inductor. When no current flows through the null detector, I3 is equals to I1 and I4 is equals to I2. Then I1 is equals to E divided by Z1 plus Z3. This is equation 3, and I2 is equals to E divided by Z2 plus Z4. This is equation 4. By substituting equations 3 and 4 into equation 2 and by solving both sides, we get balanced equation of impedance for the magnitudes Z1 dot Z4 is equals to Z2 dot Z3. This is equation 5. For the balance equation, we can derive equation for measuring unknown capacitance Cx and resistance Rx. Here R3 is the variable resistor to be balanced in the bridge, and C3 is the standard capacitor in series with R3. The unknown capacitor is compared with the standard capacitor, and under balance conditions the capacitor and its leakage resistance value are measured. The net impedance at the each arm of the bridge is given by Z1 is equals to R1 plus J0 ohms. This is equation 6, and Z2 is equals to R2 plus J0 ohms. This is equation 7. Here Z1 and Z2 are resistors whose capacitive reactance is 0. That is, Z3 is equals to R3 minus JXC3, which is equals to R3 minus J into 1 by omega dot C3 ohms, and Z4 is equals to Rx minus JCX is equals to Rx minus J into 1 by omega Cx ohms. By substituting the above values into the balance equation, Z1 dot Z4 is equals to Z2 dot Z3, we get R1 dot Rx minus J into R1 by omega Cx. This is equals to R1 dot R3 minus J into R2 by omega C3. This is equation 10. For equating the real parts, we get R1 dot Rx, which is equals to R2 dot R3. This is equation 11. Rx is equals to R2 dot R3 divided by R1. This is equation 12. On equating the imaginary parts, R1 divided by omega dot Cx equals to R2 divided by omega dot C3. This is equation 13. And unknown capacitor Cx is equals to C3 dot R1 divided by R1. This is equation 14. Therefore, from equation 12 and 14, we can determine the value of unknown capacitor and its leakage resistance. Experimentally, true balance can be obtained by varying R1 and R3 simultaneously. Admittance for the arm is written as Y3 is equals to 1 by R3 plus J omega C3. This is equation 15. In the balance equation, Z3 is replaced by 1 by Y3. Therefore, the balance equation can be written as Z1 dot Z4 is equals to Z2 by Y3. That is, Z2 is equals to Z1 dot Z4 dot Y3. On substituting and rearranging the above terms, we get R2 equals to, in brackets, R1 dot R4 divided by R3 plus C3 dot R4 divided by C1 brackets close minus J into brackets R4 divided by omega dot C1 dot R3 minus omega dot C3 dot R1 dot R4 brackets close. This is equation 16. By equating real and imaginary terms, we get R2 is equals to, in brackets, R1 dot R4 divided by R3 plus C3 dot R4 divided by C1. This is equation 17. Then R2 by R4 is equals to R1 by R3 plus C3 by C1. This is equation 13. By equating the imaginary terms, we get R4 divided by omega dot C1 dot R1 minus omega dot C3 dot R1 dot R4 is equals to 0. Therefore, omega is equals to 1 divided by square root of C1 dot R1 dot R3 dot C3. This is equation 19. Since omega is equals to 2 pi f, the resonance frequency of the system is given by f is equals to 1 by 2 pi into square root of C1 dot R1 dot C3 dot R3. This is equation 20. The bridge can be used for measuring frequency within the audio range. Here R1 and R3 are kept identical and the capacitor are normally of fixed values. Another type of AC bridge is Wein bridge. It is a variant of capacitance comparison bridge which has 4 resistors and 2 capacitors. It is important to note that this bridge does not require equal values of R and C. In one arm, we have RC combination in series, and in the adjacent arm, it's a parallel combination. This bridge is designed to measure frequency and used for measuring a non-capacitor with great accuracy. The arm in which capacitor is in parallel to the variable resistor R3, admittance value is used rather than impedance. Now we will study about inductance comparison bridge. Inductance comparison bridge is similar to capacitance comparison bridge, only difference being the replacement of capacitors with inductor. This bridge is used for measuring unknown inductance Lx and its internal resistance Rx. It has two pure resistances, R1 and R2, a variable resistor R3 with inductor L3, and an unknown inductor Lx having an internal resistance Rx. As discussed for capacitance, the impedance of an inductor can be written as Z is equals to R plus J into omega dot L ohms. This is equation 21. On substituting equation 21 into the balance impedance equation 5, we get R1 dot Rx plus J dot omega dot R1 dot Lx is equals to R2 dot Rj minus J dot omega dot R2 dot L3. This is equation 22. On equating the real parts, we get Rx is equals to R2 dot R3 divided by R1. This is equation 23. On equating the imaginary parts, we get Lx is equals to R2 dot L3 divided by R1. This is equation 24. To balance the bridge, inductive balance control is achieved by R2 and resistance balance control is achieved by R3. By altering the L3 or R3, the balance for the inductance comparison bridge is obtained. Now we will study about resonance bridge. A resonance bridge is a third category of bridge that contains a resistor Rx, capacitor Cx, and an inductor Lx in series in one of its arms. Other three arms consist of resistor only. On substituting values to bridge balance equation, we get R1 dot in brackets we have Rx plus J dot omega dot Lx minus J divided by X Cx brackets close. This is equals to R2 dot R3. This is equation 30. On equating real terms, we get Rx is equals to R2 dot R3 divided by R1. This is equation 31. On equating real terms, we get j omega dot Lx minus j divided by omega Cx, which is equals to 0. Omega square is equals to 1 by Lx dot Cx. This is equation 32. Resonant frequency of this series resonance circuit can be calculated with the following equation. F is equals to 1 by 2 pi square root of Lx dot Cx. This is equation 33. For measuring unknown inductor, a standard capacitor is varied until balance is obtained. Then Lx is equals to 1 by omega square dot Cx. This is equation 34. For measuring unknown capacitor, a standard inductance is varied until balance is obtained. Then Cx is equals to 1 by omega square dot Lx. This is equation 35. It is important to note that operating frequency of the generator should be known in order to find an unknown quantity. There are different types of detectors. Based on their application and frequency range, different types of detectors are given below. At low frequency, best detector is a vibrational galvanometer. For laboratory work and frequencies up to 100 Hz, moving coil type is most preferred due to its high sensitivity. For frequencies between 300 Hz to 1 kHz and for high voltages, moving magnet type vibrational galvanometer with remote control tuning are preferred. For audio frequencies greater than 800 Hz, headphones are best detector. It is important to note that the vibrational galvanometers and headphones do not have phase sensitivity. That means they cannot indicate whether resistance or reactance adjustment is required. At low frequencies and for high sensitivity, AC galvanometer and separately excited dynamometer having phase sensitivity are best suited. There are two conditions under which bridge is balanced. That is, equation 18 determines the required resistance ratio R1 by R4 and equation 20 is used to determine the frequency of the applied voltage. This means if we balance the resistance in the equation 18 and simultaneously excite the bridge at a given frequency in the equation 20, the bridge will get balanced. For a Wein bridge, circuit components are chosen such that R1 is equals to R3 is equal to R and C1 is equals to C2 is equals to C. For equation 18, it reduces ratio to R1 by R2 to is equals to 2 and frequency ratio equation 20 to F is equals to 2 pi RC. The bridge can measure frequencies within the audio range. The frequencies with the audio range are divided into 20 to 200, 200 to 2000, 2000 to 20 kHz range. Here, resistances are modulated to change the frequency range, and further fine control within the range is obtained by adjusting capacitor C1 and C2. If one desires to measure capacitance, in that case frequency of the operation of the AC source should be known. The bridge can also be used as harmonic distortion analyzer or a notch filter. The bridge is used as frequency determining element in audio and radio frequency oscillators. With Wein bridge, accuracy of 0.5% to 1% can be readily obtained, but since the bridge is frequency sensitive, it is difficult to obtain balance unless the applied voltage waveform is purely sinusoidal. Now we will study about digital readout bridge. With the advent of digital circuitry, there is a tremendous effect on electronic testing equipments. The use of digital circuits has helped in developing digital readout bridges. This bridge configuration, that is actual measuring circuitry, hasn't फिर से बोलना पड़ेगा. With the advent of digital circuitry, there is tremendous effect on electronic testing instruments. Use of digital circuit has helped in developing digital readout bridge. The bridge's configuration, that is actual measuring circuitry, hasn't changed much, and this system has also removed operator error while observing the reading. The diagram shown in figure 5 is of Wheatstone bridge with digital readout circuit. From the diagram, one can observe that a logic circuit provides a signal to R3, it senses the null, and provides a representing value for Rx. For routine measurement of bridges, pointer instruments are used. It is more advantageous if such instruments are made phase selective. Predominantly, pointer instruments are moving coil millimeters and are operated via some arrangement of copper oxide rectifiers and have a working range of 40 Hz to 1 kHz. Modern bridges are regularly fitted with an amplifier. A heterodyne or a beta tone detector are used for high audio or radio frequencies or frequencies above 3 kHz. For almost all bridges, impedance should be selected that best suits the bridge. An interbit transformer can help in obtaining higher sensitivity. When using a headphone as a detector, one must take precaution to eliminate any capacitance effect between the observer and the headphones. The range of moving magnet vibration galvanometer is up to 1500 Hz. As an AC detector, an electrodynamometer can also be used. Small capacitances have very large impedance, especially in an AC circuit at low frequency. And when measured in a bridge, they tend to form high impedance branch. Hence, electrometer is used as a detector and to increase the sensitivity. In this module, we studied about the AC bridge circuits. First, we looked into the classification of AC bridges in the introduction. Under the AC bridges, we studied about the capacitance comparison bridge and its variant Wein bridge. And then we studied about the inductance comparison bridge and resonance circuit bridge. Thank you.